We ended the last video with needing to do integration by parts more than once. So let's look at example 3. Let's look at one more of those. It says t squared e to the t dt. So remember we talked about the fact that you want to make sure your u, the derivative, eventually becomes a constant, because that's when you know that you get to stop. So we're going to say integration by parts, u du, v dv. So here I have t squared is my u, and you can tell the derivative, oh, let's not go there. T squared is u, and then e to the t dt is our dv. That covers everything in the problem. We have it all in u or in dv. But the problem is when I take my derivative of u, it becomes 2t dt. And that's not going to, when we did the natural log, it canceled out nicely, but that's not going to cancel out nicely here. The integration of dv is e to the t, so that's not too bad. So we have the integration of u dv, so we have t squared e to the t dt equals uv, so that would be t squared times e to the t, minus the integration of v, which is e to the t, times 2t dt. So here you can see that we've got another two set of functions being multiplied. So here we have t squared e to the t minus the integration of 2t e to the t dt. So we're going to have to use integration by parts again. Let's do parentheses around this because we have that negative that's going to need to be distributed. So we have u and v and du and dv. The nice thing is when you just have e to the t, it's a nice, easy integration every time. And this is one of the classic problems, t squared e to the t. So u is going to be 2t, and dv is e to the t dt. You can see that we've put everything in one of those places. So the integration of dv is e to the t, and the derivative of u is 2 dt. So here we have equals t squared e to the t minus uv becomes 2t e to the t minus the integration of v, which is e to the t times 2 dt. So we have t squared e to the t minus 2t e to the t plus the integration of 2 e to the t is 2 e to the t plus c. And that's your answer. But notice it took integration by parts twice to happen. So now let's look at the last technique we have in this area. If you have bounds, we just put them in. We'll do one of those in a moment. So let's look at example 4. It says the integration of e to the x sine x dx. Now, just looking at it, the derivative of e to the x is e to the x all the time, so that's never going to go away. And the derivative of sine x is cosine x, and the derivative of cosine x is sine x. So that kind of goes in a circle as you take the derivative over and over. So this technique is really important, and it's the one that we've been preparing for because I make you write the problem every time. So let's set up our integration by parts because this is definitely the multiplication of two functions, not a composite function. So let's go ahead and put e to the x in our u and then sine x dx in our dv. You're going to come up with the same answer either way, so let's just go that way. Now once you start it, maintain consistency. It'll be easier that way. So the derivative of e to the x is e to the x dx, and the integration of sine of x is negative cosine x. So we have the integration of e to the x sine x dx equals uv, so we have e to the x times negative cosine x, minus the integration of v, which is negative cosine x, times the e to the x dx. So two negatives make a plus. Let's make that go away. Well, here we see integration by parts again, so let's go ahead and do that. So we have, let's let u equal uv du dv. So let's let u equal e to the x again. So dv is going to be cosine x dx. Notice I changed these both to pluses because we had minus and negative. So the derivative of e to the x is e to the x dx. And the integration of cosine is sine x. So now we have e to the x. Let's write that again. Let's rearrange it. So we have negative e to the x cosine x. So put the negative out front. Plus, and we have uv. So we have e to the x sine x. Minus the integration of v du sine x times e to the x dx. Well, let's just rearrange this a little bit, and then we'll have the conversation we need to have. So, minus the integration of e to the x sine x dx. Do you see that this last term right here matches the opening term, the integration of e to the x sine x dx? When it feels like you're going in circles, often you are. So let's add this integral, the entire integral, to both sides. So we add it to that side, and we add it to this side. Good news, they match. So look at it this way. One integral plus one integral makes two of these integrals, right? And negative one integral plus one of these integrals cancels out. So here we end up with 2 integration of e to the x sine x dx equals negative e to the x cosine x plus e to the x sine x. And we're going to say plus c. We could have put our plus c out here. It doesn't matter where that goes. It just needs to go in somewhere by the end. So what we're going to do is we're going to divide everything by 2 or multiply it by a half. So look at it this way. We're going to multiply this by a half. We're going to multiply everything on the right-hand side by a half. So then we end up with the integration of e to the x sine x dx equals, we can keep that half. So we have 1/2 negative e to the x. We could factor in e to the x out. So we have e to the x negative cosine x plus sine x. Remember that c is not affected by the half. So this technique is, it's where you're going to solve and you're going to add this integral to the other side because you'll see matching integrals in the middle of the problem. And that's going to happen when your derivative doesn't ever end up being a constant. The derivative of e to the x never becomes a constant. The derivative of sine x never becomes a constant. So it's a technique we use regularly. Let's look at number 29. You have one similar to that in your homework. It's the integration from 0 to pi of x sine x cosine x dx. Now you might need to do integration by parts a couple times, but this isn't like the product rule where you can use 3 terms. So you can only use it. Everything has to go into x or dx. But if you remember your trigonometry, there's an important one that's going to be used a ton. Let's make a note real quick. Note, can't get my dot to happen. It says sine 2x, 2 theta equals 2 sine theta cosine theta. Do you see that kind of happening here? So we're going to make a substitution. We're going to replace sine x cosine x, but we're going to use this in the process. So we're going to take this 1/2 over and say sine theta cosine theta equals 1/2 sine 2 theta. So now we can say the integration from 0 to pi, x times 1/2, let's put the 1/2 in here, sine 2 theta, or 2x, our variable is x. We need to use x dx. So now we see integration by parts. So we have u, v, du, dv. There are different thoughts about that 1/2. It could go on the x. It can go on the sine 2x because commutative property, it could go out front. Most students are not as successful with that because they lose the 1/2 somewhere along the way. So let's put it with the x because it's easy there. 1/2 x, and then dv is sine 2x dx. So now let's talk about the integration of sine of 2x dx. This is u sub, but we're using u and v. We could use u, it's a totally separate problem. Let's let u equal 2x. So then du is 2 dx. So dx is 1/2 du. So we have the integration of sine of u times 1/2 du. This 1/2 can move out to the front because it's a constant. So we have 1/2, the integration of sine is negative cosine of u. So this gives us negative 1/2 cosine of 2x. Negative 1/2 cosine of 2x. So then we have the integration from 0 to pi. 1/2 x sine 2x dx equals uv. So we have 1/2 x times negative 1/2 cosine of 2x minus the integration of v, negative 1/2 cosine of 2x. How many of you noticed I forgot to do du? Let's go back up. What's the derivative of 1/2 of x? It's 1/2 dx. I'm so sorry about that. Times du, but it's necessary here. 1/2 dx. By the way, these two negatives right here make a positive, so that's nice. So we have, from 0 to pi. This notation gets a little messy. This is from 0 to pi. So we have negative 1/4 x cosine of 2x from 0 to pi plus 1/4 the integration from 0 to pi cosine of 2x dx. So let's come back up here over on the side, and let's say the integration of cosine of 2x dx. We're going to let u equal 2x. So du is 2 dx. You see a pattern here? Dx equals 1/2 du. So then 1/2 the integration of cosine of u du. Nope, 1/2 du. Dx is 1/2 du. This gives me 1/4, and the integration of cosine of u is sine of u. So this is 1/4 sine of 2x equals, I'm going to put a parentheses because I'm going to wait and put my bounds at the end. Negative 1/4 x cosine 2x plus, here I have 1/4 and here I have 1/4 sine 2x. So that makes 1/16 sine 2x from 0 to pi. So now we have negative 1/4 pi cosine of 2 pi plus 1/16 sine of 2 pi minus negative 1/4 times 0, so that's gone, plus 1/16 sine of 0. 2 times 0 is 0. So we have negative 1/4 times pi is negative pi over 4, and cosine of 2 pi is 1, so that gives me pi over 4, plus 1/16, and sine of 2 pi is 0, so that's 0, minus, we have 0 for the first term, and sine of 0 is 0. So this gives us negative pi over 4 for the answer. So you wait and do your bounds at the complete end. Let's look at number 39. It's an interesting problem. It says the integration from the square root of pi over 2 to the square root of pi. And it says theta to the third cosine of theta squared d theta. Looks like an intimidating problem, but you've got this. Now right off the bat, you can't do integration by parts because you have cosine of something, so that implies u sub. It's a composite function. I'm not going to use u sub because we're going to use u and v in our integration by parts, so I'm going to use m sub. Some people use different letters, it doesn't matter. So let's let m equal theta squared. So dm equals 2 theta d theta. So d theta equals 1 over 2 theta dm. Then we have the integration from the square root of pi over 2 to the square root of pi. That's not going to be fun to write over and over. And we have theta to the third cosine of m times 1 over 2 theta dm. Now this theta cancels with one of these, so I have theta squared. But notice that's also our m up here. Theta squared is our m, so let's switch that out. Let's make that substitution. So we have the integration from the square root of pi over 2 to the square root of pi. And then we have m cosine m dm, and we have a 1/2. I forgot the 1/2. Now you can see the u sub is going to be not too bad. So we let u equal 1/2 m. And dv is going to be cosine of m dm. Are you getting the hang of where those go? Because that should be getting a little easier. The derivative of 1/2 m is 1/2 dm. And the integration of cosine of m is sine of m. So then we're going to say the integration of the square root of pi over 2 to the square root of pi of theta to the third cosine of theta squared d theta. Some of you change your bounds. That's fine. Feel free. So we have uv 1/2 m sine of m. Kind of ran together. Sine of m from the square root of 2 over pi. I'm sorry, the square root of pi over 2 to the square root of pi. Minus, that's u times v, minus the integration of v, which is sine of m, du, which is 1/2, and I'm going to put that out front, dm, because it's a constant. So now we've got, from the square root of pi over 2 to the square root of pi. My pencil's a little small. So now we've got 1/2 m sine of m minus 1/2, and the integration of sine is negative cosine of m. On my paper, I skipped this step from the square root of pi over 2 to the square root of pi. So if I were doing this, I would skip it. I'm okay if you skip it. This is 1/2 m sine of m plus 1/2 cosine of m from the square root of pi over 2 to the square root of pi. Now, we didn't start off with m. We started off with theta, so we need to go back to the fact that m equals theta squared and put that in. So we have 1/2 theta squared sine of theta squared plus 1/2 cosine of theta squared from the square root of pi over 2 to the square root of pi. So this gives us 1/2. And when we plug in pi, the square root of pi squared is pi, times sine of the square root of pi squared is pi, plus 1/2 cosine, and the square root of pi squared is pi, minus, it just looks scary, 1/2. The square root of pi over 2 is pi over 2. Wrong symbol there. Pi over 2. Sine of the square root of pi over 2 is pi over 2. plus 1/2. The cosine of pi over 2 squared is pi over 2. So now you need to go back and think about your trigonometry. So we have pi over 2. 1/2 times pi is pi over 2. The sine of pi, I read the graphs. So the sine of pi starts at 0. Here's pi. The sine of pi is 1. That's not right. This is pi over 2. Sine of pi over 2 is 1. The sine of pi is 0. So sine of pi is 0. So that's going to be gone. Plus 1/2 the cosine of pi. So your cosine graph looks like this, and pi is -1. So times -1. Minus, here we have pi over 4. And the sine of pi over 2 is 1. Plus 1/2. And the cosine of pi over 2 is 0. It's this halfway point here, pi over 2. So that's going to be 0. So we end up with -1/2 minus pi over 4. And you could find a common denominator. I'm not sure what they're going to want. I'm happy with this. This is a nice exact answer. You could say -2 minus pi all over 4 and get common denominators. So I think you've seen the many ways to use integration by parts. Integration by parts is a very powerful tool. The thing that you need to watch for is where is it best to put the items in this area. If you can eventually take the derivative to be a constant, that's what starts out in your u, and everything else goes in dv. Just be sure that you're working carefully. There is a reduction formula, and it says the integration of sine to the n x dx equals -1 over n cosine of x sine to the n minus 1 x plus n minus 1 over n integration of sine n minus 2 x dx. I don't feel the need for you to prove that. It's proven using integration by parts. They say n is greater than or equal to 2, and n is an integer. So it can't be done if you have a different power. Just use your integration by parts and do the math rather than trying to memorize that craziness and where it comes from. So I hope you understand. If not, contact me, and thank you.